wait another minute or so in case there's some more joining. Okay, I'm going to go ahead and get started. Okay, I'm going to share my screen. Okay, I want to start out by announcing a news story. Okay, this week the Nobel Prize winners were announced in physics, in medicine, and in chemistry. Right, in physics, the basis of the Nobel Prize was an understanding of black holes. Black holes and the Milky Way's darkest secret. Okay, these are the individuals that won the physics prize. Roger Penrose, Reinhard Genzel, and Andrea Ghez. Right, the Nobel Prize in medicine, physiology of medicine, was based on gaining an understanding of hepatitis, and it was awarded also to 3 individuals who are listed. Harvey Alter, Michael Houghton, and Charles Rice for the discovery of the hepatitis C virus. And then the Nobel Prize in Chemistry was just announced. There we go. All right, so the Nobel Prize in Chemistry was awarded for work on a technique called CRISPR, CRSPR, which is a gene editing technique. And the 2 Nobel Prize winners in chemistry were Emmanuel Charpentier and Jennifer Doudna. Okay, so colloquially, CRISPR is referred to as genetic scissors. Okay, there's a lot of different applications of CRISPR. For example, in cancer therapies. There's also some investigation in using CRISPRs to for example, to control malaria. There's some ethical questions as to whether that might create unintended consequences, for example, to cause that variety of mosquitoes to go extinct, which is doable using CRISPR, but would that cause unintended consequences? Okay, back up here. Let's go back to Zoom here. And okay, let me see if anyone else is waiting to join. Nope. Okay. All right, before we look at ethers, okay, last time we were looking at nomenclature of alcohols. The alcohol functional group takes priority over alkenes and alkynes. Okay, so for example, if we have a compound such as this, okay, the alcohol takes priority, so that's automatically on carbon number 1. Okay, so this is cyclohexene, all, and the double bond is between 3 and 4. So 3-cyclohexenol or cyclohex-3-ene 1-all. Okay, notice we dropped the E on the ene because the next letter is a vowel. Okay, this is the newer method. Okay, I want to talk a little bit about some commercial uses of alcohols. The simplest alcohol is this one, and it is methanol in the IUPAC. Its common name is methyl alcohol. It's also called wood alcohol. Okay, because it was originally obtained way back in the late 1600s by the destructive distillation of wood in the absence of air. Okay, so methanol is the simplest alcohol, and some of the uses of methanol, it's very useful as a solvent in the organic lab. It dissolves a lot of organic compounds. It's also miscible or infinitely soluble in water. You can mix it with water in all proportions. Okay, so it's a good solvent. It is also used as a fuel. It is one of the ingredients that's been used in gasoline antifreeze additives like heat. It minimizes the chance of gasoline freezing. Okay, it's used as a fuel in racing, such as the Indianapolis race, Indianapolis 500, that uses those cars use methanol. One of the advantages of methanol as a fuel is that if there is a crash and a fire, since methanol mixes with water, unlike gasoline, a methanol fire can be put out with water. Okay, it turns out methanol is also very poisonous. There have been instances of people mistaking methanol for ethanol, consuming it. It can cause blindness, it can cause digestive distress, and enough of a dose can be fatal. There's been some news stories recently. Okay, since we're all using hand sanitizer, there have been some news stories about some imported hand sanitizers that are very dangerous because they contain methanol. Okay, another important commercially important and commercially available alcohol is ethanol. Ethanol is the IUPAC ethyl alcohol, is the common name. Ethanol comes from two principal sources. It can be obtained from petroleum refining, okay, by hydrating ethylene, and a lot of ethanol is produced that way. We start with ethylene, and we hydrate it. It's also produced by the fermentation of sugar with yeast. And the highest concentration that you can get from fermentation alone is about 12% ethanol. Okay, so wines typically contain about that percentage of ethanol. For alcoholic beverages that have higher concentrations, these are distilled. Okay, things like vodka, whiskey, and other alcoholic beverages that have a higher ethanol content. So ethanol is also a good solvent. It's a good fuel. It's added to gasoline as an octane booster. It is something else I want to mention is the term proof. Okay, proof, when talking about alcohol, is the percent ethanol by volume times 2. Now, I'm not sure the reason that they took it times 2, but 86 proof alcohol, for example, would be 43% ethyl alcohol. 200 proof would be 100% ethyl alcohol. The term goes back to the late 1700s, and it's thought to have originated in England. Whiskey merchants would water down their product by diluting it with water to increase their profits. And one of the ways that they could test whiskey to see that it had not been diluted was to mix it with gunpowder, and if it had too much water in it, the gunpowder wouldn't ignite. And so this was considered proof that it hadn't been diluted. And the other term that I'll mention here is denatured alcohol. Okay, since ethyl alcohol or ethanol is used for multiple purposes, for fuels, for solvents, and it is a component of alcoholic beverages. Alcoholic beverages are very heavily taxed, and it's estimated that, okay, depending on the location, as much as 80% of the price of alcoholic beverages is a combination of federal, state, and local excise taxes. Okay, if you're going to use ethanol for some other purpose, okay, one of the things that they can do is they can add something to make it poisonous. And if it's not drinkable, it's not subject to beverage taxes. And this is called denatured ethyl alcohol or ethanol. Probably the most common denaturant is methanol. Okay, methanol is almost impossible to separate from ethanol. And if it contains methanol, of course, it's poisonous and undrinkable. This one is 2-propanol, or commonly called isopropyl alcohol. And this is the main component of rubbing alcohol. Okay, its primary use is as a disinfectant. It's also a good solvent. And it's usually sold as either 60, 70, or 90% isopropyl alcohol with water. Okay, I read that it's most effective as a disinfectant if it's around 60 to 70%. It has to be at least 60% to be effective. And it's actually more effective if it contains a little bit of water compared to pure isopropyl alcohol. Okay, and then I've already mentioned ethylene glycol and propylene glycol. In the IUPAC, this is ethane 1,2-diol. This is propane 1,2-diol. Diol is 2 alcohols. And these are used in antifreeze and coolant. Right, let's turn back to the chapter. There we go. We're on chapter 8. Okay, alcohols associate by hydrogen bonding, and this is the principal reason for their high boiling points and, at least for the smaller alcohols, for their high solubility in water. Okay, I'll show you this slide again. If we compare, for example, methanol to ethanol, which have very similar molecular weights, there's a huge difference in boiling point, which attests to the strength of hydrogen bonding versus London dispersion forces. Okay, let me mention just briefly some of the reactions of alcohols. Alcohols are very weak acids, about the same acidity as water. Okay, they can also act as bases. The oxygen picks up a proton from a strong acid to give an oxonium ion, which is shown here. We can produce the conjugate base of an alcohol using an active metal such as sodium or potassium. This is actually an oxidation reduction reaction rather than acid base, even though we produce the conjugate base. In this case, sodium gets oxidized, it loses an electron, hydrogen gets reduced, so hydrogen gas is given off. We can convert alcohols to alkyl halides, okay, using HCl in this case. Since this is a tertiary alcohol, this reaction takes place readily at room temperature. Secondary and primary alcohols are more difficult to substitute, and they require high temperatures and concentrated HBr or HI. Okay, thionyl chloride, SOCl2, is actually a better way if we want to produce a primary halide from an alcohol. Okay, this takes place very readily. The byproducts are gases, which can easily be removed. That prevents the reaction from going backwards. Okay, so this takes place under mild conditions. You get very good yields. You can use this with primary alcohols. Okay, dehydration, we can produce alkenes from alcohols. using concentrated sulfuric or phosphoric acid. Okay, notice here the difference among primary, secondary, and tertiary alcohols as far as the conditions. Primary alcohols are really difficult to dehydrate, so this is taking place at 180 degrees Celsius. Secondary alcohol is a little bit easier to dehydrate. Tertiary alcohol, okay, notice that this can be hydrated at just a little bit above room temperature, 50 degrees. The more substituted alkene predominates. That's Zaitsev's rule, if there's more than one alkene that can be produced. Here's the mechanism. I'll go through this again. The oxygen picks up a proton from a strong acid. We get an oxonium ion. Okay, this is actually the exact same step in the SN1. Okay, this is the exact same second step in an SN1. Okay, water leaves, we get a carbocation. And instead of the nucleophile forming a covalent bond with the carbocation, what happens is a base, such as water, will remove a beta hydrogen. Okay, the beta hydrogen is on the carbon next to the carbocation. Okay, so water removes that proton. This pair of electrons then moves toward the plus charge to give us an alkene. Okay, hydronium is regenerated, so it's a catalyst. Okay, for a primary alcohol, this is actually an E2 reaction since primary carbocations are not stable. Okay, it starts out the same. Oxygen is protonated, but then water removes a beta hydrogen. We form the double bond. We kick out water, all in the same step. Dehydration is reversible. Okay, which way we shift the reaction depends on the concentration of water. Okay, if we have a higher concentration of water, okay, that's going to shift it toward hydration. Okay, to form the alkene, that is the reverse reaction, okay, we want a low concentration of water. In other words, you use concentrated sulfuric or phosphoric acid to dehydrate. All right, oxidation. I think it's useful to go over oxidation again. Okay, we can recognize an oxidation. There is an increase in oxygen content or a decrease in hydrogen content or both. Okay, when a primary alcohol is oxidized, it first forms an aldehyde. Okay, often that aldehyde is very easily oxidized. So under these conditions, the aldehyde is not isolated. It goes all the way to the carboxylic acid. The carboxylic acid has more oxygen content, less hydrogen content. So this is an oxidation. This is using chromic acid. Okay, if we want to stop at the aldehyde, okay, we instead of using chromic acid, we use this reagent called PCC, pyridinium chlorochromate. And as long as we're not doing this in water, we can stop at the aldehyde. And again, this doesn't affect the alkene groups. Okay, we talked about tertiary alcohols. Let's talk about secondary alcohols. All right, if we have a secondary alcohol, such as cyclohexanol, if we use chromic acid or PCC, either one, okay, the functional group that we obtain is a ketone. We get a ketone from a secondary alcohol. Okay, primary alcohol gives us an aldehyde or a carboxylic acid. Okay, under these conditions, it stops at the ketone. Under very severe conditions, you can break open that ring and form two carboxylic acids, but under these conditions, it stops at the ketone. Okay, and then the last statement on the slide, let's make this a tertiary alcohol. Okay, tertiary alcohols are not easily oxidized, and so here, NR, no reaction. There's no reaction that occurs. Okay, the problem with this is you have 5 bonds, and so that can't exist. Okay, I also want to mention that when you use chromic acid, there's a color change that takes place. Chromic acid solution is orange, and when an oxidation occurs, okay, this is chromium plus 6. Okay, if you do the math, oxygen is -2, hydrogen is +1. So by difference, chromium has an oxidation number of +6. Okay, so the alcohol gets oxidized, chromium gets reduced, goes from +6 to +3. So this is orange, and then it ends up as a blue-green. And so you can easily detect that an oxidation is occurring just by observing the color change. Okay, so for example, if you have an unknown alcohol, if you add chromic acid to it, if there's a color change, that tells you it's a primary or a secondary. If nothing happens, that would indicate it's a tertiary. There's also another application of this color change. Okay, it's not so much used for that purpose anymore, but the original breathalyzer sobriety tests for drunk driving used chromic acid. Okay, when the suspect was stopped, they would breathe into a tube that contained chromic acid. If there was alcohol on their breath, the color change would result. What they use now is an oxygen fuel cell to detect breath alcohol. Okay, there have also been some environmental issues with the use of chromium-6. Let's see, it was about 20 years ago, a movie came out called Aaron Brockovich. I don't know if any of you are familiar with that one, but the utility in California, Pacific Gas and Electric, was discharging chromium-6, and people were getting sick, getting cancer, dying from that. And there was a $300 million judgment in court against Pacific Gas and Electric as a result of that. We have an experiment that we do in lab where we use household bleach instead of chromic acid, and the byproducts are much more environmentally benign. Okay, the problem is we don't see a color change, but we have very benign byproducts. Essentially, salt and vinegar is what we get as byproducts. We use acetic acid and bleach, and this produces sodium chloride and acetic acid. Okay, we'll just get started on ethers today. Okay, ether differs from an alcohol in that the oxygen is between two carbon atoms. So the pattern is carbon, oxygen, carbon. The oxygen is also bent, okay, because it's sp3 hybridized. In dimethyl ether, which is shown here, the bond angle is 110.3. Okay, so pretty close to 109.5. Okay, so here's the ball and stick model. Okay, there's two lone pairs on the oxygen that are not shown in that ball and stick model. Okay, as far as nomenclature, again, the parent alkane is the longest carbon chain. We name the OR group as an alkoxy substituent. And so here are some common names. Okay, this first one, its IUPAC is ethoxyethane. Its common name is diethyl ether. Okay, it is also called ethyl ether. That's confusing to a lot of people because ethyl ether and diethyl ether are actually the same thing. And it is also sometimes commercially just called ether. Okay, so if you hear someone talking about ether, they're probably talking about diethyl ether. Okay, the one in the middle, this is 2-methyl-2-methoxy. Okay, OCH3 is a methoxy group. Okay, and it looks like this is wrong. That should be propane, not pentanol. Okay, the common name is also wrong. But this is 2-methyl-2-methoxypropane, also called tert-butyl methyl ether. Okay, this was once used as a gasoline additive. Okay, it was added. It has a really good octane rating, about 120. The problem is when it leaked out onto the ground, it was difficult to separate from water in the water treatment process. And so it's no longer used for that purpose anymore. Okay, the ether group has a very low priority as far as naming. So in the compound on the right, the alcohol takes priority. So that's an ol. And this is 2-ethoxy. Okay, so in the middle we have a methoxy. This is an ethoxy, where you have an ethyl group. So 2-ethoxy cyclohexanol. And then these are the configurations, 1R, 2R. Okay, let me back up just a minute here. Oh, let's go ahead and go on. These are some cyclic ethers. Okay, these all have common names, but their IUPAC names are less commonly used. Okay, this one is ethylene oxide. Okay, the three-membered ring. Its IUPAC name is oxarane. Okay, we have THF in the middle. We've seen THF before. And then this is 1,4-dioxane. Okay, ethers are polar molecules, okay, because of the bent geometry around the oxygen. They can't donate hydrogen bonds, but they can accept hydrogen bonds from water or ethanol or other hydrogen bond donors. And so as a result, ethers are slightly soluble in water. Okay, we are just about out of time, so I'm going to go ahead and stop there, and we'll pick this up again on Friday. Okay, your next test is coming up a week from Friday on the 16th. Okay, midterm grades should be available next week. Okay, I'll be turning those in either this weekend or early next week.